So this is your first time loading ADS. So you start by loading your software. You choose that you're familiar with ADS, and you go ahead and you create a new workspace. Make sure you create that in a directory which you can edit, and preferably one where you can go back and retrieve your folders. You would create your workspace. And once you have that in place, you can go ahead and start by creating your schematic window. We can keep that called cell 1 for now, but it's advisable to use more indicative names. Starting the simulation, you need your ports or your terminations. There are two options. You can choose one which doesn't come with a ground or one which comes with a built-in ground. So for now, we'll just use the one without a ground, and we'll add the grounds later. And as we're simulating a transmission line, so that's going to be a 2-port device, we need 2 terminations. We're going to be doing microstrip line simulations. So we search for microstrip line and we add that. And from the part search, you can also scroll down manually to finding the transmission lines, the microstrip library, and then you will find all the different layout options and the different components that would commonly be found in a microstrip circuit. Now we need to go ahead and create a substrate for our microstrip line. And considering this is a PCB technology, then this is a more suitable option from a resolution point of view. So 0.0001 millimeter is very appropriate. You'd normally go for the micron one if you're working with microwave integrated circuits or MMICs. Of course, if you prefer working in inches, and unfortunately, you'll have to be familiar with them as a unit, you could work with the mils. But for now, we'll just use a metric system and stick with the millimeters. At this point, you can define your substrate parameters. So you can choose any parameters you like. So these could match what we have in the PCBs that you'll be simulating. You've got different parameters such as conductivity of the metal layers, height of the substrate, magnetic permeability or dielectric properties, tangent delta, the loss factor, and the thickness of the copper layers. For now, we're going to populate these and leave the others. But if you double click on this menu, you can get the explanation for each parameter. And from the help function, you can read a bit more about them, which will be helpful in the future labs. So now we can go ahead and connect our lines. And because the circuit currently lacks the reference point, we can add the ground to both points. And an alternative approach to doing this will be to just simply add a line and use one ground, which makes it easier for you to keep track of the grounds. But in ADS and in the same schematic, all grounds are referenced to the same point. So whenever you're adding this short circuit symbol, you're basically shorting all the grounds to one point. Now we have the schematic. If we try and run a simulation, it will tell us that there is no simulation controller. You can follow the tutorial, but instead I'll just go straight away and add an S-parameter simulator. We've added the S-parameter simulator, and you can see it defaults to certain frequency settings. Now, 1 to 10 gigahertz with a step size of 1 gigahertz is not particularly useful. So we can double click on this and change the settings. So we can get that to match the measurements. So we can start from 0.1 to 1.5 gigahertz, and with a number of points of 3, we're not going to see much. So we can change that to 201 points, which is very common on most VNA settings, and we will press OK. With that, I can save the schematic, and we're good to go with running a simulation. That will take a while, and then you will get a plot window. And in your plot window, you can do your presentation of the results in different formats. You'll get the constants, for example, frequency, port impedance, which are what we have defined in the simulation. But ultimately, what you're interested in are the S-parameter results. So if we start by looking at the S-parameters, we can choose the S11. You'll be prompted to indicate which format you want. So we start by looking at the dB magnitude and press OK. Now you can see the S11 of your line, very well matched below -20 dB. Now we can add our forward transmission, or the S21, and we also add that in dB. And you can see that the line that's very close to 0, we cannot really see it. So one good way of doing that is to go into your line and change your plot axis to be the right y-axis. And that way you can see your forward transmission on a very, very fine scale and the S11 on a different scale. Now, of course, you can also plot your S11 as a Smith chart, which will be helpful when you want to look at the impedance. So you can see here that your result is very well matched. We can add a marker in order to make the graph more readable. And now you can see what impedance you're getting at this point. Remember that with Smith charts and ADS, the graph you get as a result you go in the marker is normalized. So for you to get the actual data, you can change it from normalized to 50. And now you can see it being converted to the actual impedance of the line. Now, if we go back and change our line dimensions, we can change that to be millimeters. We can change Rolls units, and we'll leave that as 100 millimeters, but we can change the line widths to become 4, and then we can run our simulation again. And you can now clearly see that a line with a 4 millimeter width is not matched. The S11 is above -10 at certain values, so we know that this is not the transmission line width. Now, of course, you can go and calculate the impedance of the line, but you can also extract that from the measurement from the Smith chart. One useful tool that you can use in ADS is the tuner, which allows you to select a certain parameter. In this case, we're going to choose the width, and it allows you to vary that while automatically running the simulation at the same time. So we will get our windows, we'll put both of them side by side, and we can slowly start to vary the results. So you can see now I'm reducing the width of the line, and that's improving the forward transmission, improving the reflection coefficient, which is telling us where does the line need to be in terms of widths. So we've now reached a width of 2 millimeters, and you can see the S11 is about -3. If you want to go even lower, you can change the bounds, you can change the resolution or the step size. And now you can see at this point, the line is starting to become too inductive and it's no longer well matched. So the tuner is a very quick tool that's used by most designers in order to get their design in the right space. And then you can save your values back to the schematic, and that simply helps you save a lot of steps when running a simulation. And now you can see that your variable, the width of the line, is defined as a tuner. So that's it. A quick introduction to how you run schematic simulations and S parameters in ADS. Of course, you can try different simulators and you will do that in further labs, but this will help you get started with most of the simulator functions.